Hello everyone. Today we'll talk about IPnext, which is our next generation inference platform. We're still in the early days of building it. In this talk, we'll share the challenges we are facing, the design of the system, and learnings. Today, AI is everywhere. It powers many of our productions. It is changing the world and everyone's day-to-day life. For example, AI powers recommendation systems. When we are doing online shopping, the recommendation system recommends a good product one might like. When we are watching online videos, the recommendation system may recommend interesting video to you. Generative AI is another area which is exploding. ChatGPT, for example, answers your questions and help you to do small tasks like summarization. AI also powers many other use cases like fraud detection, image classification, translation, and many more. To serve all these use cases, we deploy our training model from a training process to the inference platform, and we feed the input request and generate the inference result. This process is called AI inference. And nothing can happen without the AI inference, and AI inference requires strong inference platform. So here's a typical inference workflow. Once a model is trained from a training process, it goes to publish step. In this step, we try to do post-training optimization like model rewrites, lowering to improve model performance. Then we do a validation to ensure model quality is good. After that, the model is deployed in the inference platform. Now the production system can query the model on inference platform to get the inference results. During the life cycle of the model is typically gets retrained and republished periodically. And this step is called snapshot updates. The inference platform will ensure the snapshot updates have a smooth transition. And at the same time, sometimes when the model has multiple parts, the transition will also ensure synchronization among all these model parts. Eventually, the model may be replaced by another model or be deleted. Though across different use cases, they share a similar workflow, one of the largest challenges we met is actually the heterogeneity. There's a different perspective for it. First, model may have large variation. A model comes with very different complexity. Some model may be much more expensive compared to others. Model also come with different architecture and sizes. And also model performance could be quite differently. Some model may be compute heavy, while others are memory bandwidth heavy, for example. Second, the requirement across different use cases could be quite different. There are many aspects and trade-offs we need to consider. For some use cases, there is a very tight latency requirement. As a result, we mainly optimize for the serving latency. For some other use cases, they focus on the efficiency to reduce the cost we need to serve the model. Some other models have a tight requirement for the model freshness, which may affect the model quality. Finally, in the inference world, we also have a lot of different hardware to serve the model. Besides the CPU, there's a set of inference AI accelerators, like GPU, MTIA, and TPU. All these chips come with different performance, and we need to tune the models and the hardware to match with each other. In addition, if you look at the deployment of all these chips, there will be a capacity imbalance across different regions. When you look at a given region, you may find you do not have a certain chips for serve the certain models, or you may have one type of chips that is large enough or you have enough capacity for that to serve one models. Facing all these challenges, we are designing our new system. Next, I will transition to Hitesh to talk about the vision of our new system.
Hello everyone. Now that Chao has shared the technical challenges, let's look at our vision for the new platform. IPnext is a unified platform to manage the entire lifecycle of model deployments, from publishing all the way to serving. IPnext has a modular design that allows us to orchestrate a wide range of complex workflows all under a single system. For example, different model architectures needed for generational AI or recommendation feed could all be supported under one single platform. IPnext provides a global and highly automated capacity management that is especially crucial for inference at scale. For example, it can deploy model across numerous data center regions with heterogeneous hardware such as CPUs, GPUs, and other ASICs as Chao covered in technical challenges. Finally, it is important for any system at scale, especially AI serving systems, to provide high reliability and low latency for both request serving and model updates. Now we will cover the high-level architecture of the new inference stack. As you can see here in the picture, at the top we show users who interact with IPnext through APIs and CLIs interfaces. On the left, we have a machine learning engineer which publishes newly trained or refreshed machine learning models. And on the right, we have product engineers who want to integrate these machine learning models in a product such as ranked feed. At the bottom, we show core infrastructure that provides foundational cloud services such as container management, CI/CD, auto-scaling, and much more. And finally, in the middle is the new IPnext platform built with a collection of composable modules. For example, the metadata module is responsible to fetch dynamic metadata such as the latest model versions, and that ensures that the inference and the training systems are in sync. The planner module generates a deployment plan across multiple data centers considering heterogeneity in hardwares and regional supply constraints. Finally, the deployment module generates low-level infra specifications that are consumed by core infrastructure to materialize the deployment plan into runtime container jobs. Unlike the previous architecture, we can easily add new modules. We can compose those modules to create a new workflow for different use cases. This is all towards our vision to provide a flexible platform supporting diverse use cases. Before we dive deeper into technical details, we want to quickly introduce the data model used across all IPnext components. Firstly, an ML model is decomposed into multiple parts, which supports different requirements such as distributed hosting for large models or heterogeneous hardware hosting. Then, each part of the model can further have multiple instances, also known as snapshots, representing different versions of a model. Note that machine learning models have different requirements for how snapshot updates are handled. Some models require a stronger synchronization across the parts, while some models have more relaxed requirements of synchronization across the parts. The good thing is this generalized data model allows us to provide a common set of reusable components, resulting into a rapid development of new serving paradigm. While in previous architecture, we created new data model for each specific case, resulting into fragmented implementation and slower development. Now, I will pass it back to Chao to deep dive into technical details.
Thanks, Hitesh, to talk about the vision of the system. In this section, we'll deep dive into two examples of how we handle the heterogeneity. First, we'll talk about how we handle the heterogeneous model architectures. Second, we'll talk about how we handle the heterogeneous hardwares. As we mentioned before, models come with different model architectures, and sometimes require to serve in a distributed fashion. This could be because the model is out of the scalability limitation of a single machine. For example, there's no enough RAM within a single machine to hold the model. Potentially, This could also be because we want to improve the utilization by disaggregating different model partitions. Serving a model in a distributed fashion introduces extra complexities. First, the system needs to be able to deploy different model parts across different machines. Second, during snapshot transition, we need to synchronize across different model parts to ensure they are consistent. Finally, all model parts need to collaborate with each other to finish serving one request. Traditionally, serving a model with different distributed fashion requires a lot of effort, both from infrastructure part and the model part. This could slow down the iteration of models a lot. To address this problem, IPnext handles all this complexity within the system and allow users to serve a model with different arbitrary serving paradigms. To do so, we first try to split the model into different modules during publish stage. Each module will be materialized to a different model file. When the model is deployed, we pass a deployment graph. And following the graph, IPnext deploys different module parts to different places. You might notice a module part could also be deployed in the client side. IPnext also provides synchronization across different module parts during transition. Finally, we also add data plane support to ensure all the module parts could collaborate with each other to finish server requests. I want to highlight, within IPnext, we won't require any effort from both infrastructure side and model side anymore. All we need to do in order to serve a model with a new distributed serving paradigm is just to slightly change one config. That will largely improve the efficiency of model engineers. Next, I will pass it to Hitesh to talk about how we handle heterogeneous hardwares.
Now, let's talk about how IPnext handles heterogeneous hardware such as GPUs or custom ASICs like MTIA. Managing capacity across multiple data center regions with heterogeneous hardware is quite challenging at scale because of large diversity in the model performance across different hardware types and supply of capacity across different regions. This challenge is further compounded by the dynamic nature of traffic demand and capacity supply, which requires constant adjustment to ensure optimal alignment between the two. IPnext provides a global and highly automated capacity management, which is crucial for inference at scale. A model owner only has to provide a global capacity and latency budgets, while the platform manages all the complexity behind the scenes for the user. And model owners do not have to worry or think about the explicit regional placement and hardware types. And in all this, Planner is the key component, which is responsible to find a globally optimal placement for a large number of model deployments while respecting the various users and infrastructure constraints. Let's look at sample output from the Planner. As shown in this image, for each model, Planner outputs a placement plan across different regions with different hardware types and also the units of deployment needed to handle the workload for that particular model. Once the initial decision is made, Planner revisits its decision every couple hours. And a separate transition module is responsible for safely converging the system towards the new plan generated. Later on, this plan is consumed by the lower-level core infrastructure services to create a container runtime job. In our previous architecture, we did not support heterogeneous hardware deployments like this one. Moreover, the capacity planning was quite manual process, resulting into slower development for the overall product. Now that we looked at the technical design, we'll look towards closing our talk. As we mentioned earlier, IPnext is a new platform, and we are in early days of building it. As we learn new lessons, we will improve its design accordingly. but we do want to share a few early learnings so far in our journey. First, inference at its scale needs to support diverse workflows consisting of several moving parts. Hence, a unified platform is key to effectively develop and debug such workflows, thereby eliminating fragmentation within the platform. Secondly, the rapid pace of innovation in AI models and hardware architecture is breathtaking, and that is here to stay. We all know how LLMs broke through and changed the world. All this makes it really necessary to have a flexibility and extensibility within the platform, so in order to effectively adapt to these rapid advancements in evolution in technology. As we look towards the future, we are working to onboard most state-of-the-art AI models on IPnext, including generational AI workload. We'll also work towards supporting recently announced MTIA hardware in production soon. To succeed in AI, a scalable and flexible inference platform is a key ingredient, and our mission is to build that platform in IPnext. Thank you.